we did indeterminate form and Locator Rule before. Now we will see the variations. Variation from 0 over 0 or infinity over infinity form. And the first one is the indeterminate product. Indeterminate product. The one that gives us 0 times plus or minus infinity. Okay. If it is very close to 0 but not 0, then it becomes infinity. Okay, so the issue is which goes to infinity faster to which go to 0. Okay, and then later on we will also see indeterminate difference. Where we have infinity minus infinity, so we cannot really decide. We need to go further. Now, both of these cases, we will massage. Okay, we will rewrite to make them that 0 over 0 or infinity over infinity form. Okay, now then we have indeterminate powers. That's when we have the 0 to the 0 or infinity to the 0 or 1 to infinity. I believe in my lecture, I already explained why these three powers are indeterminate. Okay, because it's either they go to 0 or go to 1 or go to infinity. It can go to anywhere. Okay, depends on who goes to where faster. Now, to work on these, we usually do limit log, natural log of limit, which is equal to limit of natural log. Okay, we will use this strategy. Something we have done with the derivative also, right? Okay, when we compute the derivative of function to a function, we use logarithm, right? We apply natural log first, and then we do implicit differentiation. Okay, right now, we will also do it that way. Okay, so in this, when we continue later on, we will see these cases. Let's take a look, for example, what number did I do last time? I think I did up to number, 28. Is it right? I don't remember. Why infinity to the power of 0 isn't just 1? The thing is, it may not exactly 0 there. Okay, so imagine if I have infinity to the power of a little bit more than 0. That would be infinity, like 0 to from the positive side. While infinity to the 0 from the negative side, that will be 0. Okay, so imagine what happened if we have limit x going to infinity of x to the 1 over x. You see? Then that one is hard to decide because this may go to infinity, right? But if this goes to 0 faster, then whatever to the 0 will be 1. Does it make sense? Right? but whatever, like infinity to the power of slightly positive number, it will be infinity. So the thing is, will that go to 1? Will that go to infinity, or somewhere in between? We don't know. Okay, we don't know. That's why it's that's something is not clear. Okay. Now let's see further with the problems in our book, but I don't remember what was the last problem I did from the book. Let me check. The 22nd, number 24. So the last number problem I did was number 24. So let's see which one is good. Would you like to pick some problems for me to work on? Yeah, well, you pick some problems, and then meanwhile, I just randomly.
From where to where, Thomas?
Number 25 and on.
Can you do number 27?
I can do number 27. Okay, let me do number 27 first, and then you start telling me what you want me to do. Okay, now limit of x going to 0 for hyperbolic tangent of hx over tangent of x. Now the thing is, I don't know, I don't remember the derivative of hyperbolic tangent of h though. I know when you plug in x equals to 0, that will be 0 over 0 case. That one I know. Okay, so then I will apply Locator Rule. I apply Locator Rule, then the derivative of tangent x, I know is secant squared x. But I don't remember the derivative of hyperbolic tangent. So let me cheat from the book behind. It's hyperbolic secant squared. So it's the same to what we know. Hyperbolic secant squared of x. Hyperbolic secant x of x, and then both of them equals to 1 when I apply 0. So this is 1 over 1, that's 1. That's easy.
What does, I'm sorry, I have to ask, what is H hyperbolic? What is that?
That's something I skipped. That's something I skipped from 6.7, but it basically means the following. Hyperbolic sine of x actually represent the following expression that we see a lot in engineering: e to the x minus e to the negative x over 2. So it is not really a trigonometric function. They just called it a new function. It turns out that they behave quite similarly with trigonometry. Like when you do the derivative of this sine, hyperbolic sine, right? Then you will see the derivative of hyperbolic sine is hyperbolic cosine, which is e to the x plus e to the negative x over 2.
Is it something that we need to learn?
I skipped that one because I don't need you to know that.
Oh, okay then.
Yeah, all the problems that requires hyperbolic solution can be done using other method. Can be done using other method. So, for example, consequently, hyperbolic tangent of x is basically hyperbolic sine of x over hyperbolic cosine of x, which will give us e to the x minus e to the negative x over e to the x plus e to the negative of x. Seems to be ugly, okay, but the how to say that? It's like in that ugliness, there is some principle that they always stick together as if they behave like a trigonometric function.
Okay.
You know, so if you want to know more about these hyperbolic functions, you can take a look on 6.7. Okay, you can take a look on the 6.7.
Okay.
In other
Thanks,
words,
Thomas.
no problem. Do not underestimate ugly people. Okay. Like, well, honestly, if you read that further, right, from 6.7, you will be amazed how these two guys here, it starts from these two guys. It starts from these two guys. They actually behave very, very similarly to trigonometric functions, such that even when you define the tangent, it still behaves the same way. The cosine, the hyperbolic cosecant, hyperbolic secant, hyperbolic cotangent, the derivative, the sum product, half angle, double angle still behave very similarly. You know, that's I myself surprised with that. But I skipped that one because I don't really want to learn something new that we can actually solve other ways anyway. That's why I skipped this section. Okay. And I also saw that other instructor at Wesleyan College, when they asked about hyperbolic trig functions, those are basically simple ones. Those are basically simple ones. So, for example, you can see that the derivative of hyperbolic sine x respect to x, therefore, is hyperbolic cosine. Then what will happen if I replace the x by, for example, x squared? And the same chain rule applies. That would be 2x hyperbolic cosine of x squared. So nothing really new. Nothing really new. Okay, that's for number 27. More?
Can you do number? Oh wait, you said 25 and on, right?
Mm-hmm.
Oh, never mind. Oh, never mind. I think I seen you do something similar to that.
Let's see, number 34. Instead of waiting for you choosing one number, it's like easy for me to just like toss a coin and see what number shows up. Okay, so limit x approaching 0 of x over tangent inverse of 4x. Now, when I plug in x equals to 0, I will get 0 on the top, and tangent inverse of 0 is also 0. So that's a 0 over 0 form. I will apply Locator Rule. So I get on the top, it becomes 1. The derivative of tangent inverse is 1 over 1 plus blah squared times derivative of blah. Okay. Now then I need to massage that. Basically simplify such that it's not complex fractions anymore, right? So I get 1 plus 16x squared over 4, which when I plug in x equals to 0, I get 1/4. Number 36. I underestimate this question until I see closely. Oh, shoot. That's actually quite ugly. Limit x approaching 0 from the positive side of x to the x minus 1 over natural log of x plus x minus 1. Now, the thing is, unless I say it wrong, but that's x to the x, right? Yeah, that's x to the x. So the thing is like, even if I plug in 0 to the 0, it's already undefined, right? This part here, it's already undefined, right? Is 0 to the 0 is 1? Well, 0 from the positive side, that's right, that's 1. Right? 0 to the positive number. Okay, as long as it's not 0, that's 1. So we are fine with that. Okay, but then I still need to find the derivative if I want to do Locator Rule, because when I plug in x equals to 0, I get 0 for 0. Oh, then I will need to do Locator Rule. Now the bottom is easy. The derivative of natural log of x is 1 over x. The derivative of x is 1. The numerator is the one hard. What is the derivative of x to the x? So let's do a side work. Okay, let y equals to x to the x. Do you remember how to do the derivative for this? In fact, I believe I went over exactly the same question before. If you have a function of x to the function of x, then to do derivative, you need to apply logarithmic differentiation. Okay, so this is natural log of x to the x, which is x natural log of x. Then implicit differentiation, which will give us 1 over y times y prime. That is 1 times natural log of x plus x times 1 over x. So y prime is y times natural log of x plus 1, which is x to the x times natural log of x plus 1. So if I apply Locator Rule, I will get on the top here x to the x times natural log of x plus 1. I wonder how it will help. I still have that x to the x, that's the thing.
Would you want to add the the natural log to the limit?
I don't think it will work though, because my issue is still that I need to do derivative here. You know, I need to do derivative there. Let me massage a little bit. Let me massage a little bit.
I was going to say, what if you were to distribute it? Would that work? Oh, no, it wouldn't work.
Yeah. Oh, I mean, we don't know, right? But I don't think that's necessary. But let's see. Let's see. At least I want to do this. You see, when I plug in x equals to 0 positive, then I will have issue here also. This will be 1. This will be negative infinity. Right? But I will have infinity here.
Right.
Okay, so this is one of the point of trouble, right? This is one place that I get trouble. So let me multiply the top and the bottom by x. So all of a sudden, I don't know what's the answer here. I mean, I can't really tell what's the answer by just looking at that. So if I multiply the top and the bottom by x, I will get this x on the top times x to the x, ln x plus 1. And then I will have, this is natural log of x going to 0 positive of x to the x plus 1 times natural log of x plus 1 over 1 plus x. Now, the problem is when x going very close to 0, I hope you see the trouble here, this becomes what? If I plug in x equals to 0, then this will be 1, right? Okay, no problem with the denominator, but the 1 here will be basically 0 to the 1. But 0 to the 1 is 0, okay? And this guy here will be negative infinity. So we end up with 0 times infinity case. You see? That's why this problem becomes, I really hope that was a typo though. That's not an x to the x. I really hope that's x to square, but apparently not. So let's see. Let's see. I really don't know what to do from here.
If we distributed the x to the x,
how do you distribute it? Oh, you mean to the
up above? Yeah. If we distribute it to the ln x and the 1, will we be able to bring the exponent down to the front?
I don't think so, because this will be x to the x plus 1 times ln x plus x to the x plus 1 over 1 plus x. You know, we are okay here because this will be 0. This is 0, so this is 1. Right? But my issue is still here. This will be 0 times negative infinity.
What if we had done that before we, up above, before we multiplied top and bottom by x?
You mean we do another derivative? Let me go back. Let me go back. So from here, you mean?
Yeah.
So you distribute. Let's give it a try. Let's give it a try. So if I distribute that, I will get x to the x ln x plus x to the x over 1 over x plus 1. Then this will be infinity over infinity case, huh? Yeah, this will be infinity over infinity case, because on the top, like what I said here, this will be 0, this is infinite, negative infinity, this is positive infinity. This is 0. We have too many infinities here. Yeah, so it's like indeterminate on the top of another indeterminate form.
So what happens if we come across something like this? Do we just say it just?
Well, we need to go. We need to find out a way, though. It's not just like I don't know how to do it and then skip. Right? I mean,
well, I didn't know if there was like, you know, a rule or like something that said, oh, it's just undefined.
We need to know why it is undefined, even if that's what we say. You know, okay? So, like, why you call that undefined, right? Okay. And
wait a minute.
distinguish undefined and indeterminate. You know, indeterminate means we cannot tell.
Could we bring up the 1x to the numerator to where it be x negative or x to the negative power? I don't know if that would work.
Which one?
The denominator, 1x, bring
1
it
over
to the
x.
numerator.
So I multiply the top and the bottom by x.
Oh no, did we already do that? Yeah, we did.
Yeah, that's what we did.
Never mind.
Yeah, that's what we did.
Yeah.
Okay, so we will, if that's what, so this is what we did earlier, so this is what we get. At least we get that's equals to 1 at the denominator, and on the top will be x to the x plus 1 times ln x plus 1. I get a message coming in earlier. Why undefined? I don't remember which part you say undefined. But basically 0 over 0 is undefined. It can be anything.
Can we do top and bottom multiplied by natural log, and that might let us bring the exponent to the front?
So you mean you try to say that this is equals to limit x approaching 0 positive of natural log? Like this? Well, we don't have that though. The thing is we don't have that rule. Yeah, we don't have that rule. You know what? I make a very big mistake since the very beginning. I overthink this question. My apology. I did it wrong since the very beginning. I forgot one thing. I make mistake here. Let me show you my mistake. My mistake is here. This is not 0 over 0. Duh. That's not 0 over 0.
Doesn't ln x go to negative infinity?
That's right. And the thing is, this will be 0. I mean, to be more precise, 1 minus 1 over negative infinity plus 0 minus 1. That's 0 over negative infinity. That's 0. But let's prove one more thing. Okay. I need to show that limit x going to 0 positive for x to the x is equal to 1. Okay, I want to show that first because that's my assumption here though. That's my assumption here. Okay, let's prove that first. So let's compute that. Compute. So this is like a side work. Compute limit x approaching to 0 positive of x to the x. So let y equals to x to the x, natural log of y is equals to natural log of x to the x, which is x ln x. Now then, when I apply the limit of x going to 0 positive of natural log of y, that is limit x going to 0 positive of x ln x. Now, I hope you start seeing the issue here. When x going to 0, this is 0, this is negative infinity. Right? Now, then it becomes indeterminate product. Does it make sense? So I need to massage that, rewrite it into quotient. So I rewrite it like this. Now then I apply Locator Rule. I will get limit x approaching 0 positive of 1 over x over negative 1 over x squared, which becomes limit x going to 0 positive of negative x, which is 0. Okay, but that's the limit x approaching 0 of natural log of y. Right?
I need to go.
Therefore, natural log of the limit of y is 0 and limit x going to 0 positive of y, which is x to the x, is e to the 0, which is 1. Okay. Now then, so So going back to that big question, limit x approaching 0 positive of x to the x minus 1 over natural log of x plus x minus 1. This will be 1 minus 1 over negative infinity plus 0 minus 1, that's 0 over negative infinity, which is 0. Okay. In other words, what makes this problem difficult? See, my mistake, I didn't check that properly, huh? Okay, I didn't check that properly. So this big question here, actually, we need to settle this first. Once we know what value that is, then actually it's not one of the indeterminate form. It is indeterminate on this part, which we compute separately. Go on further. Number, you please tell me which one you want me to do. Otherwise, I'll just keep on going this way. Number 38.
You 40.
Number 40, okay. Yeah, number 38 seems to be simple. Number 40. Limit x approaching a from the right-hand side of cosine x natural log of x minus a big over natural log of e to the x minus e to the a. Wow, this seems to be hard. Okay, so if I plug in a in place of x, I will get cosine a, which is not a problem. Limit a positive minus a, that's very close to 0, over limit e to the a positive minus e to the a, that's also very close to 0. So this will go to negative infinity. This will go to negative infinity, while we don't know if cosine a is positive or negative. Either way, it is indeterminate form because of negative infinity over negative infinity with plus minus in front of them. Okay, so from there we see, let me keep that scratch work there. So this is negative infinity over infinity form. So that justifies us using Locator Rule. Limit x approaching a from the right hand side of the derivative of cosine is negative sine x times ln x minus a plus cosine x times the derivative of that, that will be 1 over x minus a big over the derivative of that is 1 over e to the x minus e to the a times the derivative of that is e to the x. Seriously. I really want to cry. Limit, I need to massage this first, make it nicer. So this is negative sine x limit x minus a plus cosine x over x minus a over e to the x, and on the top I will multiply by e to the x minus e to the a. You know what? Let me rewrite it this way instead. Let me rewrite it this way instead. Let me rewrite it this way. So this is e to the x minus e to the a over e to the x. And then the denominator, e to the x should be on the denominator. Yeah, I have e to the x on the denominator. Yeah, I put it there. Okay, so let me shift this down a little bit. Maybe I rewrite this there. I rewrite this. So on the numerator, I will have negative sine x natural log of x minus a plus cosine x over x minus a times the whole set that did. From here, I don't really know what to do.
Can we break apart the original equation?
Like,
Move a and x separately?
e to the x and e to the a separately?
Yeah.
Now, the thing is, that's actually one point of contention, though. If we separate that, then you will not see the zero. Right? That's actually the source of zero. What makes it, so let's see the problem. Okay, this will give us negative infinity. Okay, this will give us infinity because you have zero at the bottom. And this will also give us zero.
Right.
Right? Okay, so if you tell me to move this out, then it's okay, because this is basically, I can write this is a 1 over e to the a limit x going to a positive of e to the x minus e to the a. You see what I mean? Like, in other words, this is something I can bring out without change the value of limit. You know what? Let's do it this way. Let me go back, because this cosine x is troublesome. I think I attacked that way too early. I don't need to. I'm sorry. Okay, let me go back. That is not the source of problem. my cosine x. So let me just bring that out first. What do you think? So that I don't need to worry about that guy. Okay, this guy is not a problem. Okay, let me kick you out. So this is basically limit x going to a positive of cosine x times limit x going to a positive of natural log of x minus a over natural log of e to the x minus e to the a. Does it make sense for now? And I can easily change that cosine x becomes cosine a, right? Because the limit is okay. Our issue is here. This is our issue. Is it okay so far? When I replace x by a for this cosine x, it doesn't give me something strange, right? Okay, it doesn't give me something strange. The one here will give me limit 0 positive, and this is limit 0 positive also. But how fast each one of them approaching 0, is it possible that the top one going to 0 faster than the bottom one? We don't know. Okay, so that's where I will do my Locator Rule. So this is where I get my infinity over infinity case. So this is equal to, at least this is cleaner than what we had earlier, limit of x going to a positive of 1 over x minus a, big over 1 over e to the x minus e to the a times e to the x, which will give us cosine a times, now I massage that, limit x going to a positive of, oh yeah, yeah, so this is e to the x minus e to the a over e to the x times x minus a. See, right? Now, the nice thing is this is actually constant. So this will be constant later on. Right? That will be constant later on, such that when I do the derivative, we expect that to disappear. Let's do so. This is still 0 over, when I plug in here, 0 over, yeah, we still have 0 over 0. That one will be 0 over 0, please. So apply Locator Rule again. I will get cosine of a limit x going to a from the positive side. On the top, I get e to the x. At the bottom, I will get e to the x plus e to the x times x minus a. Which I can factor the e to the x and cancel. Right? Cosine a limit x going to a positive of e to the x over e to the x times 1 plus x minus a. Ooh, wow. Okay, cancel this guy. Let's cosine a limit x going to a positive of 1 over 1 plus x minus a. Now I plug that in, that will be just cosine a. Oh, wow. Unexpected. Yeah, because this guy is 1. Okay, let me look back. Is there any issue so far? Oops. So my first step is I see this guy, this is not a problem, so I separate that, right? And I basically localize the issue. This is my issue. When I do the derivative on the top and at the bottom and massage that a little bit, I do Locator Rule, so the constant here disappear, and then I need to do product rule here. That's why I get this. But then on the denominator, I have common factor e to the x, which I will cancel. Then after that, I apply the limit x approaching a. So I think I want to write it this way before I get that final answer. Let me write this. This is equals to cosine a times 1 over 1 plus a minus a, like that. Okay, which is cosine a times 1 over 1, which gives me that. That's number 40. I usually do this problem this way, like when I kind of like confuse what I did, I look back to the question and then ask myself, what slowed me down earlier? Okay, and then you notice that this has not been a problem since the beginning, which when I did the derivative, remember when I did the derivative earlier, it actually just messed up the whole work. Okay, while when you plug in x equals to a here, it actually gives you no problem at all. Right? So that's the one slows me down. And once I separate that out, it seems like taking care of this is just simple. Just doing the Locator Rule twice. Okay, that's one number 40. Let's see number 42. You see even number 40 seems to be still limit of quotient, right? Limit of quotient. But number 42, now we have indeterminate form, indeterminate product case. Indeterminate product case. Limit x approaching infinity. Oh, okay. Infinity of square root of x, this will go to infinity, times e to the negative x over 2, which will go to 0. Okay, so this guy go to infinity, this guy will go to 0. Infinity times 0, that's indefinite, indeterminate form. But the fix for this case is actually quite easy. Just rewrite that as a quotient. So in this case, I will write it as square root of x over e to the x over 2. Okay, and then apply, then you will see, you will have now infinity over infinity form. Right, then I apply Locator Rule. Limit x going to infinity on the top. When I apply Locator Rule, I get 1 over 2 radical x. At the bottom, when I apply Locator Rule, I get, I'm sorry, when I do the derivative, is e to the x half times 1/2, right? Which will give us limit x going to infinity, the 1/2 cancel, get the bomb, get the boom, 1 over x, square root of x, e to the x over 2. Now, you will have 1 over infinity at the bottom. Number 46. Limit to infinity, x goes to infinity of x times tangent of 1 over x. Again, this goes to infinity while this goes to 0. I think the answer is 1. That's infinity times 0. That's equals to limit x going to infinity of tangent 1 over x over 1 over x. Right? Now it becomes 0 over 0 case. So now I apply Locator Rule. So before you apply Locator Rule, it has to be in form of quotient first. Okay. Now then the derivative of tangent is secant squared of 1 over x times the derivative of 1 over x is negative 1 over x squared. While the one here is negative 1 over x squared. Notice that the negative 1 over x squared cancels. That's basically limit x goes to infinity of secant squared 1 over x, which will give us secant squared of, what is 1 over infinity?
Isn't it 0?
Okay, what is secant squared 0? I need to use calculator, Thomas.
Oh, it's 1.
Okay. Now, remember I look at that question and say right away, oh, the answer is 1, right? But I didn't do all of this actually in my mind though. I didn't do that. Let me tell you my little secret, what I did in my mind to get that one so early, so fast. Once I rewrite it, notice that when x goes to infinity, then what happened to 1 over x?
Doesn't it go to 0?
It goes to 0, right? To be more precise, 0 positive. So that limit can be rewritten as limit 1 over x goes to 0 positive of tangent 1 over x over 1 over x. Or if I use dummy variable, that's limit t goes to 0 positive of tangent t over t. But that's something we learned in calculus 1. When x going to 0, the ratio of tangent x over x is just 1. I mean, you don't need to use Locator Rule. That's something we have known even in calculus 1. Okay, in calculus 1 we learn limit x going to 0 of sine x over x is 1. Limit x going to 0 of tangent x over x is equal to 1. Okay, so the blue one, I actually use this green color here. But if some people just like it long and hard, that feels good. Okay, number 50. They make it in red color, so maybe there's something interesting there. Limit x approaching 0 of cosecant x minus cotangent x. Now, both of them is undefined though. Yeah, both of them undefined. So undefined minus undefined is so undefined. Instead of doing it this way, let's break it up a bit further. This is 1 over sine. This is cosine over sine. Do LCD. 1 minus cosine x over sine x. Then you see when I plug in x equals to 0, I will get 1 minus 1 over 0, which is 0 over 0 case. Right? So I apply Locator Rule, limit x approaching 0 of sine x over cosine x. That will be 0 over 1, which is 0. How about number 52? I think that is quite similar, but I don't know. Number 52, limit x approaching 0 for cotangent x minus 1 over x. That will be, both of them undefined. Let me rewrite it first. So this is cosine x over sine x minus 1 over x. Do LCD so that we can put them together. This will be x cosine x minus sine x. And at the bottom we will have x sine x. I wonder if it helps. It's like this is full of 0. This is 0 minus 0 over 0 times 0. So if somebody asks, would you like a lot of zeros in your account? Maybe not. So I will do Locator Rule. On the top, I will get cosine x minus x sine x minus cosine. Oh, that's really nice. Not bad. Right, I did product rule here. So the derivative of this give me this. Right? Okay. On the denominator, however, when I do product rule, I will get sine x plus x cosine x. But then on the top, something cancel. On the top, something cancel. We get negative x sine x over sine x plus x cosine x. Doesn't help.
Thomas,
Mm-hmm.
wouldn't that be 0 over 0 again, or no?
In this case, this will be 0 over 0 again.
So can we apply the hospital again?
I have that in mind, but I kind of wonder if that will help. But, okay, let's do that. Let's do that. Locator Rule. It's a French though, so we don't read the S. Okay, so that will be negative sine x minus x cosine x. At the bottom, we'll get cosine x plus cosine x. Oh, maybe that's the one help us. Minus x sine x. Yes, that's actually the one helping us. because then when now I plug in 0, I will get 0 minus 0 over 1 plus 1 minus 0. Thank you. Number 54. This one is actually on the easy side. Yeah, we need some easy question for now. X going to 1 from positive side, from the right hand side of natural log of x to the 7 minus 1 minus natural log of x to the 5th minus 1. I hope this is on the easy side. This is equals to limit x going to 1 from the right hand side. Difference of log equals to log of quotient. And then limit of log equals to log of limit. But then the one inside here, you see this is 0 over 0 case. Under the condition of limit, right? So I apply the Locator Rule on that limit. And I will get 7x to the 6 over 5x to the 4th. Get the boom. Natural log of limit x going to, what am I doing? I can just plug in 1 right now, huh? Duh, it's not 0. The limit's not going to 0. The limit goes to 1. So when I plug in x equals to 1, I will get natural log of 7/5. Duh, Thomas. Okay, long time not seeing easy questions. Number 56. I think I will do number 56 and then number 62 and then number 66. Number 56. I try to catch ugly questions. Wait, Shane, you make a comment. I thought I was doing it right. Which one you're talking about? Were you the one telling me that we should do another Locator Rule here? Is it what you were referring?
Yeah, but I was talking about when you're moving on from the next step. I thought it was just ln 7 over 5, but then you kept going, and I was like, oh.
Yeah, it's
No,
ln 7 or 5. Yeah.
Yeah, but before you kept going, and I got confused.
I thought the x going to 0.
Oh,
I
right.
thought the x going to 0. So
Oh, and you even wrote that down. I didn't see that.
yeah, see, I thought it's x going to 0, but it's x
Okay.
actually going to 1, not
Right.
going to 0. So I almost make a mistake there by that. Man, that 1 is so small, huh?
I was almost confused there too.
Yeah, so yes, you did right. You say natural log of 7/5, right? So you did right.
Yeah. Perfect. Thank you.
Number 56, limit x going to 0 positive of tangent to x quantity to the x. Now, this is the one I said that you have 0 to the 0 case. And when you have the indeterminate power, you need to use natural log. So you need to say let y equals to this ugly function. It's like you don't like your x. What happens if you see an x on the top of an x? Apply natural log. So that is natural log of tangent to x, quantity to the x will give me x natural log of tangent to x. Now then I will apply the limit of natural log of y equals to limit x going to 0 positive of x natural log of tangent to x. When x goes to 0, I get this is 0. Tangent becomes 0, but natural log of 0 is negative infinity. Okay, so that gives us the case of 0 times negative infinity case. Therefore, I need to rewrite it a bit further. So on the top, I will use natural log of tangent to x. At the bottom, I will use 1 over x. Now, sometimes you will wonder who should go to the bottom. Just try one by one. Okay, but we usually like to have polynomial at the bottom, or in this case, 1 over x. Now, on the left-hand side, however, limit of natural log, we can switch. Okay, but you need to explicitly show that in the step. Okay, so I will show limit of natural log is natural log of limit. Okay, now then on the top and the bottom both goes to infinity. Then I apply Locator Rule. This is, oh, what is the derivative of natural log? That's 1 over, huh? That's 1 over tangent to x times the derivative of tangent is secant squared 2x. Derivative of 2x is 2. Big over derivative of 1 over x is negative 1 over x squared. This will give me natural limit x going to 0 positive of, you know what, I bring the negative to the super front. We bring the negative here. Okay, and then rewrite them. I get 2x squared secant squared of 2x over tangent 2x. Now I can say the answer is 0. How do you get that, Thomas? By just looking at that. Sorry, I don't have no negative anymore here. So the answer is 0. Do not do Locator Rule anymore. Please don't. You will mess it up so badly to the bad. Just so badly. I don't think that's what you want to do.
Wait, so could you show us how this is? I thought it was 0 over 0 again, or no?
It is 0 over 0 again. Yeah, but you can massage that without and get the answer 0 without using Locator Rule actually. Okay, let me show you first how to do it with how to massage that. I think what I will do is this. Secant is cosine squared, right? 1 over cosine squared. While tangent on the denominator will give me sine at the bottom and cosine at the top. No square. So far, is it okay? So the secant squared becomes this. Okay, and then the tangent to x now becomes this.
So,
My purpose is so that I can cancel one of the cosine.
so you're just breaking up those two. I mean, at this point, couldn't you just do the rule again?
Not yet. I can simplify. It's like I don't want to rush into simplify like Locator rule, because if you do Locator rule here, it's like the derivative of this times the derivative of this. It's like
It gets
derivative of
messy.
this.
You're
It
right.
gets so messy. It's
Yeah.
better for me to simplify first.
Okay, I understand
Okay.
that.
Okay.
That's a good
It's
point.
basically, if your life is not that simple, don't have a kid. Let me tell you this. Let me tell you this. Why I use that terminology. Don't have a kid. In Indonesian, like Indonesian language, the word derivative that we use, derivative in math, actually means, in Indonesian, the word derivative is called turunan, which means descendant, literally means descendant. Okay, so what I was trying to say earlier is like, if your life is still messy, do not have any descendant. You don't want alimony thing. Now, my teacher in Indonesia, the one saying that. Okay, if you are still at school and still struggle with your calculus 2, don't try to have any kid. That's what he was joking about.
Don't try. Yes,
Huh?
don't try. Say, yeah, don't try.
It's just so hard. Well, anyway, so I will cancel one of the cosine. Even at this point, I don't think you want to do derivative. At least, I don't think you want to do Locator rule, because this is quite messy if you do Locator rule here. But you notice that this is actually half of sine double angle. Let me show you. If I multiply the top and the bottom by 2, this becomes negative limit x going to 0 positive of 4x squared over sine 4x. Now, at this point, if you want to do Locator rule, go ahead, which I do not, I still say no need, actually. Okay, you can do Locator rule. Let me use dot, Locator. But I show you alternative way. Alternative way, you see it this way. This is equals to negative limit x going to 0 of 4x times x over sine 4x. Why do you do that? Well, because limit x going to 0 positive, this guy here is equal to 1. That's negative limit x going to 0 positive of x times limit x going to 0 positive of 4x over sine 4x. Okay. So when x going to 0 positive, then 4x will go to 0 positive also, right? Okay, that becomes 1. And that's basically, this is negative 0 times 1, that's 0. But on the left-hand side, we have natural log of limit x going to 0 positive of 1. Therefore, limit, I'm continuing from here. You see, on the left-hand side, we have this guy. We are not done yet. We have this guy. Therefore, limit x going to 0 positive of that tangent 2x to the x, which is our y, is equals to e to the 0, which is 1.
So if you presented this like a problem like this on a test, I haven't had a chance to check your previous tests yet for calc, but would you be okay? So you'll be okay with us leaving it where we had it negative 2x squared secant squared of 2x over tangent 2x without going this far? Because it's
you need to go on. You need to go on. You need to
go
show
on,
me.
okay.
Yeah, you need to show me. Okay. Yeah. So.
Oh, so if I
So
did
the one here is not clear. The one here is not clear.
right.
Right.
I
The one
didn't-
here is not clear. What I did was like for me to, I tried to simplify first. So I break it into cosine and sine, and I cross my
without
finger.
going into the L.
I cross my fingers that something simplified. Now, if you want to do Locator Rule from here, I wish you very good luck.
Okay.
You know, it's again, it's like do not do derivative without simplifying it first.
This is a lot of work for one problem. Wow.
Welcome to Calculus 2.
Yeah.
Yeah, welcome. That's why since the beginning I keep on saying that learn to show work, because it's really about your patience in showing work, though. Like the long journey will not be an issue if you know just do one thing at a time. It will be a lot nicer if in between we know what to do along the way, right? Okay. It's just like, oh, can we just keep on doing Locator Rule? You can, but you see in this case, so you will notice that when we have trigonometric situation, keep on doing Locator Rule will not solve your problem if you don't simplify it in between. You see, imagine when we have this question here, where's that? Look up, somewhere. Where's that? The one here. Imagine if I didn't cancel this cosine x and minus cosine x. If you keep on doing the derivative again, that's just fugly, right?
I have a question, Thomas.
Uh-huh.
So I feel like sometimes I get lost while I'm showing the work. I mean, besides practicing, would you have like a tip for me to knowing where to go, like in terms of like the steps needed, or do I mean, the only thing you would say is practice?
Okay. To be honest with you,
Yeah.
I have no answer for that.
Okay.
Because I myself at times get stuck. You can see from what I do here. Right? Okay. So yeah, and I hope you also see that when I do problems in class like this, I don't prepare. I mean, I just learn from the of course I know what the book says, right? Okay, but I do not look at the solution manual and then present it to you as if I already know it, as if it is something natural for me. No, because when I do the problem, I try to replicate your situation. When you are the one taking the test, what you will do. Okay, so we try to do things in natural way, in the sense that it makes sense, right? You see what I'm saying? So in other words, when I break this secant and tangent in terms of sine and cosine, it may not be something you realize you can do, but that's actually still something natural to do. We did do that in trigonometry class. Does it make sense? Right? So it's actually still something natural, not something like, oh, you know what? That's a trick that I never see. You may not ever see that, but that's not something out of nowhere. You know, it's like it's something we did before. So I try to replicate those kind of situation. Like I purposely not preparing, so that when I do the tests, do the problems in class, I can try to think from your point of view, not from someone who already saw the solution. Okay, and I can tell you that in the last 5 years, I look at the solution manual maybe only 2 times. And one of them is because somebody say, Thomas, you have different answer. and I check my work, I don't see mistakes. And I check the solution, then the solution manual, then I see my mistake. Oh, I missed something here. It was something so small with this, like something like this, because I don't write down the positive, approaching from positive side, then I get it wrong. Something like that. Okay, but again, I don't really check solution manual, because when you look at the solution manual, you will feel a couple of things. You will feel as if you are so stupid. Why this person just do it so easily and I don't get it when I first look at the question. Okay, while when the person actually wrote that solution, that person actually think hard for the question too. Okay. In other words, when you look at the solution manual, you cannot replicate your natural way of doing problems and how to come up with idea. Oh, you know what? I can do this. Oh, you know what? I can do this. Okay. So no, don't. I do not think you should feel discouraged that when you get stuck. That's part of the learning process. You see?
Thank you.
Okay. And yes, like what I said earlier, that sometimes we get stuck because we just don't simplify enough at the beginning. Like somewhere in between, we can simplify and we didn't, and we just hit it all the way right away. Like for example, the one here, I just do Locator Rule again without realizing if I simplify that it will be a lot easier, right? So yes, don't feel discouraged, and that's where having group study becomes very helpful. Because you may be super smart, but you don't see some simple steps.
Question,
Mhm.
that part you had just circled where it's 2x squared secant squared x. Couldn't we apply the limit product rule and pull out the 2x squared and then just take the derivative of secant squared 2x over 10 2x?
You can try. You can try. But the way I see it will get so messy that I don't think you want to go to that direction. Yeah, it will be very messy. It will be very, very messy. Okay? Yeah, it will be so messy. Such that I don't see any, how to say that, any light at the end of the tunnel. Okay? So I didn't try that, but I don't think that's how I will approach it. If I can simplify, I will simplify first. Okay? Yeah, simplify before it gets so messy. So in fact, anytime you see it start getting messier, try to simplify first before you go on to the next step. That's for number 56. Number 60. Limit x going to infinity of x to the natural log of 2 over, oh wow, over 1 plus natural log of x. So this is a function of x to the function of x. I think that's what I will do also. I will apply natural log and then do the limit. So let y equals to x to the ln2 over 1 plus ln x. Applying natural log, then I get ln2 over 1 plus ln x times ln x. Now apply limit both sides. Limit x going to infinity of natural log of y equals to limit x going to infinity of natural log of 2 times natural log of x over 1 plus natural log of x. Oh, you know what? Natural log of 2 is just coefficient. I can bring it out. No problem. The thing on the far right factor is the one with trouble. You have infinity over infinity there. Right? This is infinity over infinity case. Does that make sense? On the left-hand side, however, that will be natural log of limit x going to infinity of y. I will apply Locator Rule, so I get natural log of 2 times limit x going to infinity of 1 over x big over 1 over x. That's just 1. Natural log of 2 times limit x going to infinity of 1. You need to write this part though. You need to write this. Okay, let me warn you. You need to write this. You need to write that. In other words, it's already equals to 1 even without x goes to infinity. Okay, don't just write 1 right away, because if you write equals to 1 right away, okay, you are saying that when you plug in infinity, 1 over infinity big over 1 over infinity equals to 1, which is not true. Okay, remember, if your limit notation suddenly disappear, it means you plug the variable, the value of the variable in, right? But that's not what you're saying. This person is dead on arrival. This person is already 1 before you apply the limit. Does it make sense? Okay, so then it will be limit 2, natural log of 2, while on the left-hand side, we have natural log of x going to infinity of y. Applying, canceling the log, then I have limit x going to infinity of that ugly expression x to the natural log of 2 over 1 plus natural log of x equals to just 2. Right now is 8:48. Let me take a little break. We come back at 9 o'clock. Okay, and I still have at least one more problem I would like to do. I have number 58 that I really want to do. Out of so many questions that I want to do in this section, number 58 is something I always do. Did I do this number 58 in my lecture, by the way? Anybody watch the lecture? Did I do this problem? Well, I think I should check that myself. I didn't do that in my lecture, the recording. Oh, you
No,
didn't.
sorry, I haven't watched your lecture yet. So,
Oh, next time watch it first.
yeah, it's
Next
a
time
lot of
watch it.
math in one day.
I know, I know. Now, what I say is like try to watch that during the weekend. That would be better. Well, anyway, take the break first. We come back at 9 o'clock. Now, since some of you have not watched the lecture video, let me ask you to please do so. Please, maybe use what? Use the word what? Note or warning? Note. Please make sure to watch the lecture video lecture video 3B. That's the second lecture video for week 3 and 4A by Monday. Okay, this is the thing. This is the thing. Especially in that 3B, I mentioned something very important about integration by parts. And it shortcuts a lot of work that we need to show if we do integration by parts conventionally, okay, like long way. Now, I want you to learn what I show you there that I called a tabular method. And that method is not mine though. That method is not mine. That method is, I learned it from my professor. And that method was actually quite well known in the past, but recently not a lot of people know that. In fact, that tabular method is taught only by, is mentioned only in Thomas calculus. George Thomas, not me Thomas, no. In other words, if you try to look for it in a lot of calculus textbook, you will not find it. Okay.
There's also this YouTube guy called Organic Chem Tutor,
Yeah.
and he does a
Yeah.
good video on it, I think, as well.
On using tabular method?
Yes.
Yeah. The only people using tabular method must have learned it somewhere, sometimes from Thomas calculus. Okay. By the way, as far as I know, George Thomas, the person who wrote this Thomas calculus, already passed away. He wrote this book a long time ago, and what happened is then less and less people apply the tabular method. The explanation is a bit long, but once you see, oh, this is what actually happens, then it becomes a lot faster. Okay. So that's why what I will do today, I will basically just finish up this 6.8. And then on Monday, when we come back, I will continue with 7.1. But at that time, when I do 7.1, I will just do problems, and I will use tabular method in general. Okay. I will emphasize which integral you need to memorize. Like the integral of secant cube is something you need to memorize. Okay, but you will see that when I went over 7.1 in my lecture. Okay, what happened when I did 7.1? If you see, I did 7.1 in my lecture 3B, and I go over that again in my lecture 4A. Now, the reason it becomes longer because in 3B, I need to explain it with conventional method, and then I start with tabular method. At the beginning of lecture video 4A, I do some problems with tabular method. So I did a lot of problems there already on this tool, right? What I would like to do is on Monday, I will do problems, but only use tabular method, which then supposed to be faster, and hopefully we can do more problems that way. Okay, instead of spending time on something quite obvious that you can learn on your own. Okay, instead of doing conventional stuff, let's see the beauty of integration by parts. Okay, let's do see that. So what I will do today, I will basically, let me cancel this 7.1. We'll go on with only this 6.8. Now in this 6.8, with the rest of the time we have, around 40 minutes, we can do 2 more problems, but let me show you first number 58. Number 58. Number 58, and I hope you realize later on why I emphasize this so much. Why I emphasize this so much. Will I ask you this type of question in your test? Maybe not, but in long run you will see you need, this is a limit that you have to memorize, at least by heart. 1 plus a over x to the b to the x. I will do it long way first, and then I will turn around and show you another way to do it. Okay, so we will try with a solution. Let y equals to 1 plus a over x to the power of bx. Therefore, the natural log of y is natural log of that expression which means I can bring the bx to the front. Apply limit both sides. And you will see that limit of 1 plus 1 over x, when x goes to infinity, this will go to 1, and limit natural log of 1 is 0, while this part here will go to infinity. I definitely can bring the b out. So let me take the b out. At the same time, I will rearrange the x to the denominator. Okay, so let me take the b here. Let me mark it. This is the b. Now it's here. And on the numerator, I have natural log of 1 plus a over x, big over 1 over x. Okay. While on the left-hand side, we have natural log of limit now. Limit of natural log equals to natural log of limit. And I will apply Locator Rule, which will give me at the bottom negative 1 over x squared. On the top, 1 over 1 plus a over x times the derivative of a over x, which is negative a over x squared. The negative cancels. Over x squares also cancel. So I have a over 1 plus a over x. Is it right? But when x goes to infinity, I will get a over 1 plus 0. So this is equals to a times b. Let me continue here. Therefore, limit of x going to infinity of y is equals to e to the ab. In other words, limit x goes to infinity of 1 plus a over x to the power of bx is e to the ab. Okay, alternative way to do this. From section 6.4, number 64. So I want to quote something we have done before. In fact, I did that in class. I did that with you also. 6.4 number, I'm sorry, not 64, number 94. Number 94. At that time, we have this show that limit n goes to infinity of 1 over x over n to the power of n is equals to e to the x for x a positive number. We did that one before. Okay, we did that one before. Let me change now the x becomes, let me change the x becomes 1. Okay, for x equals to 1, we will get limit n goes to infinity of 1 plus 1 over n to the n equals to e to the 1 or simply e. if you take financial math, this is how they define E. It's a definition. It's a definition. Okay, they define it this way. There are many ways to define E, but this is one way to define it. Of course, another look of this limit notation, instead of using n, I can use x. Agree? When x goes to infinity, then 1 plus 1 over x to the x is equal to E. Is it okay? No. In fact, to do the problem above, we can just use this though. We can just use this. I don't want to. I don't want to. I want to use this basic definition that I have here. I will start from this. Okay. I want to use this fact. When x goes to infinity, then this expression is equal to E. Now, then we go back to that number 58. From 6.8. Limit x goes to infinity of 1 plus a over x to the power of bx. This is what I will do. I will rewrite that a over x to be 1 over x over a. Is it okay? That's the same thing, right? And even further, I would like to rewrite that exponent x. I would like to rewrite that exponent x becomes b times a times x over a. Is it okay? But at the same time, if x goes to infinity, assuming a is positive, okay, assuming a is positive, then x over a also goes to infinity. Is it right? A b times x over a. Now that expression then becomes, if I use dummy variable, limit t goes to infinity of 1 plus 1 over t to the power of t to the power of ab. This is limit t goes to infinity of that expression, quantity to the power of ab, that is e to the ab. Okay. But this approach requires the a to be positive. What if the a is negative? Then we cannot use that here, because the assumption is what happens if a is negative? Then this becomes negative infinity. You see? Okay. There are more things to say, but you will see similar case when A is negative, but some adjustment should be made. The reason I emphasize that here because when I did my undergrad in math, I also took some econ classes. To be more precise, it's a business classes. I double major in math and business. And when I did my PhD at USC, I also taught at their business schools, like the calculus and statistic classes. I saw that the professors there, just like in my undergrad when I did my business major, they also emphasize this a lot, okay? Because we see this a lot in econ, in finance. The way we defined that earlier, we defined it earlier is by, where did I write it? Here. The way we define it, we use x goes to infinity. Notice that this expression is actually the same to limit. Let me use t instead. T goes to 0 positive, 1 plus t to the 1 over t. This will also give you e. I basically changed that x becomes 1 over x. When x becomes 1 over x, right? Then the infinity becomes 0 positive. So we suddenly get another definition of E, which is just another loop. Okay, now looking back. Notice that in number 58, I actually used that definition. Okay, I can just go ahead right away from number 98, section 6.4, number 98, where we have limit n goes to infinity of 1 plus x over n to the power of n. This is e to the x. Right? Okay. So what happens if x equals to a? Limit n goes to infinity of 1 plus a over n to the n equals to e to the a then. Is it right? Now I change that n becomes x. That's still e to the a. I just play with the variable. I don't like n, change that to my x. Right? Okay, now then apply this on the left-hand side. To the power of b. But limit b to the power of b of limit is limit to the power of b. Bajang, we are done. So notice that I did problem number 58 in this 6.8 with 3 different ways. Only the first one I used Locator Rule, which is the longest word. Right? That's the longest word. If you know something, how important is what we learned from that 6.4, then you see it happens again and again and again. My professors in the past once asked this kind of question, similar to this, not exactly the same to this. So his homework was the following. Let's say number 66. I just use an example. Okay, limit x going to infinity of 2x minus 3 over 2x plus 5 to the power of 2x plus 1. And he said use compute this, evaluate that using Locator Rule and using the definition of E that we had above. The second part is more challenging. But after we really work it out, it's actually just like, hey, well, that's okay. You know, okay. Now, so let's do this one more problem, and then I go home, sleep. I'm already at home. All I need to do is sleep. But let's do this. One more problem. Let y equals to, because this is a function of x to the power of function of x, right? So we have to use natural log before doing the limit. So natural log of y will be 2x plus 1. Don't forget to use parentheses. Natural log of 2x minus 3 over 2x plus 5. Now apply limit x going to infinity of natural log of y is equal to limit x goes to infinity of natural log of quotient over 1 over 2x plus 1. Okay, I hope you follow me in writing. If not, can you tell me what will be a natural step after this? I don't think I will do Locator Rule right away. The reason is because the derivative of this will be kind of painful. I know I need to do a quotient rule. I mean, it's doable if you want to go ahead. But I think what I will do instead, I will split it first.
Yeah, can you split into two separate limits?
Yeah, that's what I think I will do first. So I will rewrite that as natural log of 2x minus 3 minus natural log of 2x plus 5 big over 1 over 2x plus 1. Then I will do Locator Rule. Okay, because we now have a super ugly case. We have infinity minus infinity over 0. It can be anything. Yeah, it can be anything. Right? So then from there, I do Locator Rule. I will get limit x approaching infinity of 1 over 2x minus 3 minus 1 over 2x plus 5. I forget the 2. Big over 1 over 2x plus 1. I will factor the 2 out. Okay, and then I will have 2x plus 1 times 2x plus 5 minus 2x minus 3 over 2x minus 3, 2x plus 5.
I have a quick question, Thomas.
Uh-huh.
How'd you get the 2 over 2x minus 3 and the 2 over 2x plus 5?
When I do the derivative, I need to do chain rule, the derivative of 2x minus 3, right?
Got it.
Okay, so the derivative is the reciprocal times the derivative of that 2x minus 3.
Got you. Thank you.
Likewise. Okay. Yeah, and then so when I factor the 2, then 1 over 2x minus 3 minus 1 over 2x plus 5 becomes something like this. this is equal to 2 times limit x goes to infinity of, on the top I will have 8 times 2x plus 1 over 4x squared plus 4x minus 15. Don't forget, on the left hand side, this is actually natural log of limit already. And I really don't want to do it this way. It's like just a long way. But I will do it. So this is 16x plus 8 over 4x squared plus 4x minus 15. To avoid having in x that becomes infinity, I will divide each term in that fractions, in that rational expression, by x squared. So I get 16 over x plus 8 over x squared over 4 plus 4 over x minus 15 over x squared. Well, basically then when I plug in x equals to infinity, I will get 0 plus 0 over 4 plus 0 minus 0. That's 2 times 0, which is 0. Therefore, limit of x going to infinity of 2x minus 3 over 2x plus 5 to the power of 2x plus 1 will be e to the 0, which is 1. That's if I use Locator Rule method. So basically natural log, and then you rewrite that such that you can apply Locator Rule and then undo the natural log, right? Okay. Now, how about doing it without Locator Rule? So another take for this number 66 without Locator Rule. So suppose I say try to do it without using Locator Rule, but you can use the definition. So limit x goes to infinity of 2x minus 3 over 2x plus 5 to the power of 2x plus 1. This is what I will do. Notice that the denominator is 2x plus 5. So let me try to catch plus 5 and then minus 8. Is it okay? And then the one here, I will do 2x plus 5 minus 4. What do you think?
Wait, sorry, Thomas. Could you explain that again?
I basically rewrite this 2x minus 3 as 2x plus 5 minus 8.
Oh, you just what do you call it? Massaging it.
Yes.
Okay.
Okay, so this guy here, oops, this guy here becomes this. But why do you want 2x plus 5, Thomas? Because I want to catch 2x plus 5 on the denominator, such that inside that grouping symbol, I can write it as 1 minus 8 over 2x plus 5. Okay, and then 2x plus 5 minus 4. Is it what I really want to do? Now this guy becomes limit x goes to infinity of 1 minus 8 over 2x plus 5 to the power of 2x plus 5 times 1 minus 8 over 2x plus 5 to the power of negative 4.
Sorry, Thomas. Could you explain how you get there? Because I don't.
Blah to the a minus b is equal to blah to the a times blah to the b, minus b.
Oh. Got it. Okay.
Okay. I somehow start thinking that did I make a mistake on the question on my work here? Give me a second. I need to check this. The answer is 1. Why that's not what I get there? Unless I did some miscomputation somewhere. Check my work here. I start questioning that I may have done something not correct here. Good thing I show my work so that I can check it easily. Nah, I see my mistake. Duh. Okay, I make mistake here. I make a big mistake, actually quite big mistake. I make a mistake here. Notice that I apply Locator Rule here. So I get this and this, right? I do the derivative. I forgot to do the derivative here. Do you see that? See, when I did the derivative on the top, I get this, right? When I do the derivative at the bottom, that's not what it's supposed to look like. Dang, good thing I did it. Good thing I checked my work. Otherwise, I will not find my mistake. Okay, let's fix it. It's not too hard to fix. I think this one is okay. So this will be, let me fix it. It becomes negative this thing square times 2. Okay, it will cancel these 2. That 2 at the bottom will cancel with the 2 at the top. I will have negative, and I will have squared. So I will have negative here, but I will have squared here. Okay, so let me correct the top one. This is supposed to be 8 times 4x squared plus 4x plus 1. It's negative 2. That's negative. I can pull the 8 also out, so this becomes -8. Dividing the top and the bottom by x squared, let me clean it up. If I divide the top one by x squared, I will get 4 plus 4 over x plus 1 over x squared. Now it becomes, I'm sorry, good thing I checked that with another way, otherwise I will not see that mistake. So this is -8 times 4 plus 0 over 4 plus 0 plus 0. That's just -8. Okay. Therefore, this will be e to the -8. That's the answer. Yeah, I forgot to square it here, so let mark. I made a mistake here. If I didn't check that again without Locator Rule, I will not see that problem. Okay, let's see down here. How do I know that the answer should be e to the -8? Because of the following. Notice that this guy here, when, well, let me just separately write the limit. The second part later on will be just 1 to the power of -4, which will just be 1. Now the thing is, the one here, this is limit 2x plus 5 will also go to infinity, right? If I use dummy variable t, for example, limit t goes to infinity of 1 minus 8 over t to the power of t, this will be -8. But on the left-hand side, we have natural log of limit x goes to infinity of y. Hold on. No, that's not what we have on the left-hand side. My bad. I actually wrote something wrong here. It should be e to the -8 here. This is e to the -8, not -8. That's e to the -8. So the final answer is e to the -8. Yeah, not on the left-hand side. Yeah, because if we trace back on the left-hand side, we don't have anything but the original question. Okay, so limit x goes to infinity of that 2x minus 3 over 2x plus 5 to the power of 2x plus 1. Now, you may argue that, Thomas, I don't see why this guy is equal to this. I don't see that, Thomas. Fine. If you don't see that, let's do it a bit longer.
Isn't that from what you gave us earlier, the one that when it's 1 minus 1 over t?
The one I gave you was actually limit. Let's say u goes to infinity of 1 plus 1 over u to the u. This is the one equals to e. Okay. But of course, there are a lot of ways to do this. You will be able to see if I change this to a here. If I change that to a, then this will be e to the a.
Yeah.
right?
And the
Okay.
reason why it would become like e to the -8 is because, well, you have that
Yeah, this is
minus 8 over 2.
So this is limit t goes to infinity of 1 plus -8 over t to the power of t,
Yep.
right? Okay.
Mhm.
Well, I rewrite it that way. That's why then you see that's e to the negative. Oh, dude, if I didn't do this second way, I would have done this work here incorrectly. This also means the one thing, though. It also means one thing. Simply because you have a more advanced method like Locator Rule to do this doesn't mean it becomes easier, right? Okay, number 58. Yeah, it's from number 50. No. Number 58 is something else, actually. You can use that also. Yeah, you can use that number 58 expression also. If you use number 58, I was referring to this one earlier when I said definition of E. But from number 58, yes, you can use that also. Number 58, we have this result that limit 1 plus a over x to the power of bx, that's equals to e to the ab. Okay, so in this case, the a is -8, the b is 1. Right? The a is -8, and the b is invisible 1. Does it make sense? Yeah, I prefer the later method too. Now, of course, then that was a homework. I remember that was a homework which he gave us. My professor gave us, like how to say that. My professor usually just gives suggested homework. Also, okay, try to do this problem from the book. Try to do this problem from the book. And all of a sudden, okay, this is the handout, a homework that I need you to turn in. I was like, what? And we all like, can we work together? I said, well, go ahead, work together. Of course, he gave like some little points for that kind of homework. But that actually surprised me that even I keep on thinking that once you need calculus to do that, then you cannot do it other way. And he just say, nah, that's not true. That's not true. There are problems in calculus that you can do easier by just looking at the same problem in different way. That's basically what he said. Okay. Now, anyway, I will stop there. The suggested homework, I believe, given in my lectures, right? And keep in mind that on Monday, I will do that 7.1. Where is that? Yeah, I will do that 7.1, which you can see from lecture video week 3B and week 4A. I will do 7.1 and most of 7.2. I don't think I can finish those two sections in one day. Okay, but I will emphasize integration by parts 7.1 heavily, especially with tabular method. Okay, so I hope at that time you already know how to do tabular method. We just learn to apply that even more on Monday. Okay, then see you on Monday.
Thank you. Have a good night.
Good night.
Take care and stay